Okay, this course is being taken, by some engineers, by some physicists, and also by people who have might have not as much of the mathematical background as the rest of people. So I moved some of the mathematical development into the part which we usually call it the digging deeper. One of those concepts is the concept of linear and exponential growth. Linear growth there are two ways that some quantities in nature can increase. One is the linear growth. That means the amount of the resource increases by the same amount every year. Just imagine that you have a piggy bank and you put $100 every year inside in the piggy bank. Okay, piggy bank. In the first year you put $100, second year you put another $100, you have $200 in it, third year you have $300, fourth year you have $400, and so on and so forth. If you plot the amount of the money in the piggy bank as a function of time, it will show you a linear increase. However, if I take this money and put it in the bank will give us a slightly different interest. Let's say I have $100, I put it inside the bank, and the bank will give me 10% increase every year. So if I put $100 in the bank, the next year I would have $100 plus 10% of $100, which is $10 in interest, so I would have $110. The following year I will get the interest out of the $110 that I have, or 10% of that is $11. So the following year, the year number 2, I get $11 in addition to $110, so I would have $121. And this one will continue. The year after that, I have $12.10. So the amount of increase would be increased exponentially. This, if you look at it over a long period of time, can add up to a substantial increase in amount, that we have. In the beginning, the differences might not be very pronounced, but over a long period of time, exponential increase will show us a substantial increase. Many phenomena in nature are having exponential growth. The nature works exponentially. One example of that is the population of the rabbits. If you have 2 rabbits and eventually they would have a couple of more children, the children will grow up and they become parents themselves. So we have 4 children, and 4 children, they might have another 5 or 6 kids, and this numbers increases, and very, very soon you will have a whole lot of rabbits, until something happens in nature and nature intervenes and stop the increase in the population of the rabbits. Same thing is with the spread of disease. You might start the disease from a single, maybe microbial infection, and then this will start to spread, and very, very soon it will basically be occupying much of your body would be infected with this disease. Water lilies, another example. You will have water lilies can increase over a pond, maybe in a matter of few days they will be doubled. Then in another few more days, then this double will be doubled again, and pretty soon it's going to cover the entire pond. The increases could be positive or negative. That means not only it can increase, but also it can decay. Radioactive decay of the isotopes, they look like that. If, for example, you have a source of the nuclear substance, an isotope, over a period of the time, some of these nuclei will start, to disintegrate. As the size of this decreases, then the disintegration would be accelerated. So you would have a negative decay. So we can have in the natures, the linear growth is present, but not as prominent. For example, the number of the tree ring, it could be usually a linear growth. Every year there will be additional ring in the trees, and so on and so forth. Okay, or increase of the water pressure with the depth. As you go deeper and deeper, then the water pressure increases. If you go 10 meter deep, the water pressure will be twice as much as we go 5 meter deep. If you plot the linear growth on a graph paper, on a linear graph paper, you will see a linear line. However, if you take the it's a exponential growth, then it looks like an exponential, like the red curve in this diagram on the left. If you use a semi-logarithmic paper and we plot the same diagram on the semi-log paper, then semi-log paper, same growth will appear as a linear line. So that's the main distinction between the linear growth and the exponential growth. One equation which is very, very useful, and we use it in this class, is the time that it takes some quantities that increases exponentially double in its size. The equation is given here. It is the number 70 divided by percentage growth rate. Let's, for example, assume that you have every year your money increases by 10%. That's the interest that the bank will give you. So if I take the 70 divided by 10, that will be 7. That means in 7 years, the money that you put in the bank will be doubled in values. So if I put $100 in the bank, in 7 years, my money will increase to $200. In another 7 years, that means in 14 years from now, that money will be doubled again. So 200 becomes 400. After 21 years, I will have 800. After 28 years, I have 1600, and so on and so forth. If you continue doing this, after 10 doubling time, my money has been increased by a factor of 1000. So if I put $1,000 in the bank, after 70 years, which is 10 times the doubling time, that means 10 times 7, my $1,000 has grown to about $1 million. But it takes a long time before we become a millionaire. Now, most of the banks, they give only 1% or less than 1% interest. That means the money that we put in the saving account will double in 70 years. 70 divided by 1 is 70. In this example here, I'm asking in how many years would the US population double. US measures its population every 10 years. That's called the census day. Comparing the 2010 census with the 2000 census, we see that the population of the United States has increased by 13.2%. That means on the average, in a period of 1 year, the population has increased by 1.32% or about 1.3% every year. So if I take the 70 divided by 1.3, that means it's 54. In 54 years from now, then the population, or from year 2010, which we measured it, the population from 300 million will go to 600. That will be year 2064. I would suggest at this time that you look at the link below and look at an excellent talk by Al Bartlett. He's a professor and he gives many examples of exponential growth in a very seminal talk, that has been been visited by a lot of people. I downloaded from the YouTube, and you can directly look at it here, and that gives you a lot of insight into what it means to follow exponential growth. The next few sections, I talk about the art of approximation. It is very important for all of us to be able to have a reasonable estimate of events. For example, if I tell you how many people fit into this room, you have to be able to, to make a certain assumption, and based on that make some kind of approximation. So that's called an art by itself. In this question, I'm asking what's the thickness of one sheet of the ordinary paper. Okay, you don't have to be exact, but you should have a good idea of which of those answers would be the closest to the answer, whether it's 1 micron, 10 micron, 100 micron, or 1 millimeter. You should have some reasonable assumption of how to estimate those. Maybe one way to do that is take a stack of 100 paper and then find out how thick that is, and from there you can find out what is the thickness of one sheet of paper. Also, in science we often have to round off a number. I've seen students, they come up with a number I ask them to do some calculation, they come up with 16 digits. Those 16 digits doesn't mean anything. Just because your calculator shows up to 16 digits doesn't mean those 16 digits are significant. Okay, so if I tell you, calculate, maybe the money is only significant up to 2 digits. We have $1 and cents, but doesn't make much sense in talking that you have the money in the bank of $3,200 and $1,756,798. That doesn't make any sense. So rounding off has its own rule. I would suggest that you read the book chapter and do the examples at the end of the chapter. And doing some math with the significant figures is also very, very important. How to calculate the area, a cross section of a pipe, if you know the radius of the pipe, how good that number is, and how many significant digits we can use. Your ruler, you can only read it to a certain number of significant digits. I cannot read the lengths of 5.345678 meter with a ruler. At the best, I can read it within a tenth of a millimeter. So it is important that you look at this and make some intelligent guess of the number of the significant digit and how to use those in the equations. Thank you.